Welcome to the next part of our course, where we will focus on serial communication. In this section, we will first understand what serial communication is and how it works. Next, we will go over some of the most common serial communication standards, like RS-232, UART, and USART. We will see how they differ and where it's used in real-world applications. Finally, we will learn how to configure and set up serial communication, including settings which are essential for reliable data transfer between devices. By the end of this section, you will have a solid understanding of how serial communication works and how to use it effectively in industrial or embedded systems. Now, let's talk about one of the most common forms of serial communication, RS-232. RS-232 has been widely used in the electronics industry because it's simple and doesn't require much hardware compared to parallel interfaces. It was developed by the Electronic Industry Association and the Telecommunication Industry Association under the standard called EIA TIA 232E. The main purpose of RS-232 was to allow communication between data terminal equipment, like computers and data circuit, like modems. It was first introduced back in 1969 in the United States and quietly became a foundation for many communication systems. Even though newer standards exist today, RS-232 is still used in many industrial and embedded systems due to its reliability and simplicity. Here, we can see the RS-232 connector and pin configuration. RS-232 typically uses a 9-pin connector, also called a DB9 connector. Each pin has a specific function that allows two devices to exchange data properly. For example, pin 2 is used to receive data, while pin 3 is used to transmit data. The ground pin, number 5, provides a common electrical reference between the two devices. Some pins are used for control signals, like RTS and CTS, which help manage when data can be transmitted. Others, like DCD or RI, are used for modem communication. Understanding these pins is essential when setting up or troubleshoot serial communication connections in electronic systems. Let's look at why RS-232 is still a popular choice in robotics and industrial systems. First, it's very easy to implement. You only need 3 connections: transmit, receive, and ground. That makes setup simple and quick. Second, RS-232 is a universal standard, supported by almost all microcontrollers, PLCs, and computers. This makes it easy to integrate devices from different platforms. Third, it's low cost. The cables and connectors like DB9 or DB25 are inexpensive and easy to find. And finally, RS-232 supports long cable lengths, up to around 15 meters, without major signal loss. This makes it ideal for distributed robotic systems where devices are spaced apart. So overall, RS-232 offers a simple, affordable, and reliable solution for many robotics applications. Next, let's look at two other important serial communication standards, UART and USART. UART stands for Universal Asynchronous Receiver Transmitter. It defines how data is sent and received serially using just 2 main lines, one for transmit, TX, and one for receive, RX, along with a ground connection. In UART, data can be sent in different modes. Simplex, that means data goes only one way. Half duplex allows both sides to send but not at the same time. And full duplex allows both sides to send and receive simultaneously. Data in UART is sent in frames, which include start bits, data bits, parity, and stop bits. However, UART is slowly being replaced in many modern systems by faster and more efficient protocols like SPI, I2C, Ethernet, and USB. Though it's still widely used for basic and reliable serial communication. Let's look at why UART is such a useful communication method in robotics. First, simplicity. UART only needs 2 main data lines, TX and RX, which makes it very easy to implement. It's also supported by almost every microcontroller, so it's compatible with a wide range of systems. Second, flexibility. UART or USART can communicate directly with many types of devices, like sensors, actuators, and wireless modules, make it very adaptable option for robotic applications. Third, real-time communication. It allows quick and continuous data exchange between the main controller and peripherals, which is critical for real-time decision-making in robots. And finally, low power consumption. UART is energy efficient, making it ideal for battery-powered robots or mobile systems. In short, UART offers a great balance between simplicity, versatility, and efficiency. Now, let's look at another important serial communication protocol, the Serial Peripheral Interface, or SPI. SPI is a synchronous communication protocol, which means data is sent in sync with a shared clock signal. It's mainly used for short-distance communication, especially in embedded systems. It works in a master-slave architecture and usually uses four main lines: MOSI for sending data, MISO for receiving data, SCLK for the clock signal, and CS or SS for selecting the slave device. SPI allows full duplex communication, meaning data can be transmitted and received at the same time. The main advantages of SPI are its high-speed data transfer and simple hardware connections. However, it has some drawbacks. It doesn't include built-in device addressing and needs more wires than protocols like I2C. Overall, SPI is fast and efficient for direct communication between microcontrollers and sensors or memory devices. Let's quickly look at the main advantages and disadvantages of SPI protocol. Starting with advantages, SPI allows high-speed data transfer, making it one of the fastest serial communication methods. It also uses simple hardware connections, which means it's easy to set up between microcontrollers and devices. Another benefit is that SPI does not require start-to-stop bits, so data transfer is straightforward and efficient. However, there are a few disadvantages. SPI has no built-in addressing system, so each device needs own chip select line, which increases wiring. And comparing to I2C, SPI generally needs more wires, which can make connections more complex when you have multiple devices. Overall, SPI is great for speed and simplicity, but less ideal when you need to connect many devices. Now let's look at another very common serial communication protocol, the I2C, which stands for Inter-Integrated Circuit. I2C is a multi-master, multi-slave communication system that allows many devices to share the same two communication lines, SDA for data and SCL for the clock. Each device connected to the bus has a unique address, so multiple sensors or modules can communicate with the same controller. Some of the main advantages of I2C are that it only needs two wires. It supports several masters and slaves, and it has a built-in addressing system. However, there are also disadvantages. I2C is slower compared to SPI and slightly more complex to manage, especially when many devices share the same bus. Overall, I2C is ideal for short-distance communication between chips and sensors within the same circuit board. This diagram shows how communication works for I2C bus system. As you can see, there are two main lines, SDA for data and SCL for the clock. All the devices, both master and slaves, are connected to the same two lines. Each device on the I2C bus has a unique address, which allows the master to communicate with one specific device at a time, even though they all share the same connection. In this example, we have two masters and three slave devices. This setup shows one of I2C's biggest advantages, that you can connect many devices using just two wires, keeping the wiring simple and organized. This makes I2C ideal for systems like robotics or sensors on a microcontroller board, where space and simplicity are important. This slide shows an example of how RS-232 communication is used in robotic arm robot control system. Here, the central controller communicates with the robotic arm using an RS-232 serial communication. The controller sends commands, for example, movement instructions like pick and place, and also receive feedback about the arm position or status. The connection is made through a standard RS-232 cable, usually with a DB9 or DB25 connector, and can work reliably over distances of up to 15 meters. The control software plays a key role. It translates high-level instruction into RS-232 protocol signals that the robotic arms can understand. This setup demonstrates how RS-232 provides a simple, direct, and dependable communication link for precise motion control in robotics. This slide shows how UART communication can be applied in an automated guided vehicle, or AGV system. At the center of the system is the microcontroller, which acts as the brain of the vehicle. It uses UART connections to communicate with different modules. For example, it connects to the motor driver to controller, For example, it connects the motor driver to control, the vehicle movement to an ultrasonic sensor for detecting obstacles, and the GPS module for navigation positioning. Each of these devices exchanges data with a microcontroller using simple TX and RX lines, making UART an easy and reliable way to manage real-time communication in AGVs. Because UART is lightweight and widely supported, it's an ideal choice for low-cost, efficient robotic vehicles that need constant sensor, feedback, and motor control. Let's go a bit deeper into UART communication works inside an automated guided vehicle. A system startup, the main microcontroller sets up the UART configuration and sends a ready signal to all connected modules to confirm they are active. During the sensor data collection, the ultrasonic sensor sends distance data to detect obstacles. The MU provides orientation data and the GPS module reports the vehicle position. The decision-making and motor control stage comes next. The microcontroller processes all the sensor information and decides the right speed and direction for the motors. In some systems, there are also remote communication, where wireless module sends telemetry data to control station. Finally, error handling ensures safety. For instance, if the ultrasonic sensor detects an obstacle, the vehicle can immediately stop or change direction. This demonstrates how UART provides reliable and efficient backbone for coordinating different modules in an AGV. Thank you for watching this video.